Okay, molar volume. We have been using the equation, or we just learned the equation, PV equals nRT. That's our ideal gas law, all right? I guess I can just doodle right on here for those who are listening. So we've been working with PV equals nRT. PV equals nRT. And it's called the ideal gas law, and it essentially defines a gas. Now, when it comes to doing chemical reactions in a laboratory, it turns out that pressure and temperature tend to be constant. Because when we do an experiment, it's normally done probably in an afternoon, and unless the weather changes greatly on you during the experiment, then the atmospheric pressure is constant, and the temperature of your laboratory is constant. Which means the only thing that can really change, let's say when you're producing a gas, is the volume. So you can produce a gas, we can do the downward displacement of water, we can get the volume. And because the other two units are constant, because temperature is now constant, it is a constant, and pressure is constant, then the number of moles is defined solely by the volume. So when it comes to doing a chemistry experiment or studying a gas in the laboratory, volume really means moles. And because we've been using these particular, not properties, but particular temperatures and pressures that we call standard temperature and standard pressure, we can actually do a shortcut so that we don't have to use the entire equation PV equals nRT. So, molar volume, what is it? Let's define it. It is essentially the volume of 1 mole of any gas at STP or SATP. So right now, what I'm going to get you to do is I'm going to get you to use the ideal gas law, all right, to find what the volume of 1 mole of a substance is at STP. I'm going to divide this up right here. So we'll do STP on the left, and B we'll do SATP on the right. And tell me what the volume is. Let me explain maybe a little clearer. We're going to use PV equals nRT, and I've just told you that N is going to be 1 mole. And if we're at standard temperature and pressure, what is the temperature? And what is the pressure? Well, you tell me. What is standard temperature? Not standard ambient. That's the other one. That's the one in the lab. This is standard temperature. Yep. 0 degrees Celsius, which we're going to convert right away to 73 Kelvin. Pressure, standard. Yep, 101.3 kilopascals. So what I want you to do right now is substitute in your N, your T, your P, and solve for the V. I'll follow along with the calculation in a moment. Let's gather the data up for the other one I'm going to get you to calculate. Again, 1 mole. What is standard ambient temperature? Nick? 25 degrees Celsius, 298 Kelvin, 298. And what's standard ambient pressure? Yep, 100. 100. So hopefully at this point you've written down your PV equals nRT, you're substituting things in, you're dividing off the ones to isolate for V. And that's what we want. We want the volume of 1 mole. I don't have a whole lot of room, so I'm going to start substituting in. I'm isolating for V. I'll fill in the next one as well. And I'll take the numbers when you have them. Nick, which one are you giving me? STP? Yep. Very nice. I like that one. And the other one. Yeah, Nick, what do you got? I don't like 24.7. I'm hoping it would round to 24.8 because that's what it, yes, all right. 24.8 liters. All right, what does that mean? Well, that means if we get a question and we're asked to say, find the volume of so many moles of gas, and it says in the question at STP, we don't need to use the ideal gas law anymore because we actually have a special number for the volume of 1 mole of a gas at that temperature and pressure. So now we can write down a new conversion factor. Molar volume at STP. So I've got MV subscript STP, and that is 22.4 liters, and because it was in 1 mole per 1 mole. That's a conversion factor. So if the gas is at STP, I don't use PV equals nRT anymore. I use that number. And that number's on the back of your periodic table. You don't have to memorize it, but you have to realize that you have to use it. Molar volume at SATP is 24.8 liters per 1 mole. All right? So that allows me to go from moles to volume of a gas at those special conditions. If it's not at those special conditions, then I still need to use PV equals nRT, and I need to solve for V or for N, and we'll do more problems with that tomorrow. But if it is at those special conditions, then we've got a shortcut. All right? There is the molar volume there, and there we wrote that down already. There they are there, conversion factors. An important thing, it's true for any gas. All right? These volumes are true for whatever the gas is. It's independent of the identity of the gas. Right? If we were to compare this unit right here, if we were to compare this with something we've already looked at, like molarity or the concentration of a solution. If I've got a gas here, right, then that's going to be true for any gas. But if I have a solution that has something dissolved in it, then I'm going to use molarity. And that molarity, for example, might be 1.5 moles per liter. Now take a look at how these things are different. Molarity will convert from moles to liters, just like a molar volume. But look at for molar volume. The number is with the liters. 22.4 liters is in 1 mole. So they'll be used in a different, capacity when we start flipping things around. If you look at the molarity, the number goes with the moles, and that's in 1 liter. Okay? For the gases, this is true for whatever the gas is, whether it's oxygen gas or methane gas coming out of the gas taps or chlorine gas. That will always be the conversion factor. For a solution, my concentration right here is determined by the person who made the solution. It's dependent on how the solution was made. It's determined by what mass was put in there, and every solution will have its own different concentration. And so I need to be told that information if I'm dealing with a solution. I need to be told what that concentration is unless I'm looking for it. In a gas question, if it says SATP or STP, then I'm automatically able to use the appropriate conversion factor. I don't even need to know what the gas is. I just use it. Okay? Right there is a little graphic there. You can see there, that's 22.4 liters, and that's about 11 2-liter pop bottles. So if you imagine 11 2-liter pop bottles, that's 1 mole of a gas. Any gas. So that box, if we were to look at it, you know, yay big, right, yay deep, right in front of you, right about there, right there in front of you, 1 mole. And in the air, it's a mixture of nitrogen, oxygen, argon, various things. Okay? All right? Okay. Let's now, you don't have to write that down. We can use the molar volume as a conversion factor. You know, this means we don't have to use the ideal gas law if we're told the conditions. You can write that down. There's 4 quick examples. And it is as easy as you might think. We're going to convert moles to liters. It's at SATP, so you're going to use the molar volumes. I'm hoping we're getting the hang of these conversion factors. I'm starting with moles, and it really doesn't matter. Oh, I didn't want red. It really doesn't matter what the identity of the gas is. 0.024 moles times. I want to have volume on the top. I'm dealing with SATP. There's SATP, 24.8 liters per 1 mole. And that'll tell me what the volume is. No need for PV equals nRT. A lot easier and quicker than that. And we're liking 0.60, 0.60 liters. Next one, going back the other way. Starting with liters, how many moles? This time I'm having it at STP. Use the other one. Put it as a conversion factor. 5.6 liters. It's STP. I need to get rid of liters. I want moles. 22.4 liters per 1 mole. How many moles we got there? Yep. 0.25 mole. And it doesn't, oh, it says oxygen gas. Well, we didn't need that. We don't need the identity unless we're finding a mass. The next one we're going to be looking for a mass. We'll string 2 conversion factors together. Whoa. So what's the mass of 12.5 liters of nitrogen gas at STP? Now, way back when we started this process, I would make these little maps, and then we put the maps under the equation when we were doing stoichiometry. I guess I could bring that back. We're starting with volume of a gas, and that's at STP. And now I need to state that I'm talking about a gas because I guess in theory I could be talking about an aqueous solution, and I might need the concentration, but we got a volume of a gas, and what can I convert the volume of a gas to? Nick? Using what? What's my conversion factor called? Molar volume. That's right. So making our map, we would go from volume to moles using the molar volume. And now I want to get to the mass. Goodness gracious. Do we know a conversion factor to convert moles to mass? Molar mass. Very good. Little, not the best, you know, in unison type thing, but that's all right. Molar mass. And again, we don't need to write that down unless, you know, you need that to think that through. But it is quite straightforward. 12.5 liters, molar volume at STP. I need to get rid of liters, 22.4 liters, 1 mole. Molar mass, and 2, I believe, what is that? 14 times 2, 28 grams per mole. I need moles on the bottom because I need grams out. 1 mole, 28.0 grams. What's the mass of that gas? Nick? 15.6? 15.6 grams. One more. Now in this one you might think, well, we haven't been given any information. Okay, well, we've been given SATP, and we know it's methane gas. We've got the formula. But what does that have to do with density? Well, in the past when I've taught this, I've tried to get you to write the units down and think it through. But in this case, I find it's just as easy to tell you what we're dealing with here. First, let's start with a density equation. Way back in grade 9, you maybe put a rock in some water or something and it displaced some water, and then you weighed the mass and you did all that stuff. You measured it. You calculated density. The equation for density Yeah, Amber? Mass over volume. Very good. Mass over volume. You'd be surprised how quick you forget that. Well, like I said, in the past I've tried to get you to work it through and think it through, but I'm just going to give you the equation. Instead of dealing with just a general mass and a general volume, the equation will still work if I deal with 1 mole of a substance. In other words, if I take the molar mass and I divide it by the molar volume of that gas, then I still have mass over volume units in the end. I'm simply just using 1 mole of the substance as my sample. So for the density of a gas, take the molar mass and divide it by the molar volume, and you have the density at that particular, temperature and pressure. In this case, SATP. Molar mass of CH4. 4 times 1 is 4. 12. What is that? 16 grams per mole. 16.0 grams per mole divided by, and this is SATP, 24.8, and this is liters per mole. And if you cancel out the per mole, you have units of grams per liter. That's a mass and a volume unit. That is a density value. 0.645 grams per liter. That's not a large, that's not a large density in any way. If we were dealing with water, it actually has 1,000 grams in a liter, because each milliliter is a gram. But gases are not dense. That's why they're up there and the water's down there, because they're very low density. There's a lot of space in between the particles. Okay, so at this point, that's the homework that goes with this little section on molar volume.